Hello everyone, my name is Lydia. I will be covering body plan with locomotion. This covers limbs, movements, and skeletal structures. So in Module 3 and 4, Dr. Vandenbrooks talks about the important changes to locomotion and skeletal design that allowed the vertebrates to access land habitats. This was moving out of water was not simple. There were physical changes and hurdles to overcome, with gravity being the most influential force. In the water, buoyant properties allowed animals to be supported by the water, reducing the demand for moving their masses throughout their skeletal frameworks. Coming onto land, vertebrates no longer had the support system of buoyancy to counteract their body weight, and instead gravity provided a constant force on their body masses, which required new structural support and locomotive behavior. Dr. Vandenbrooks discussed gravity as a bigger issue as animals come out on land because they do not have the buoyancy of the water anymore, so they have to come up with new ways to be able to support their bodies. This gives an important point about the evolving pressures of living life on land upon skeletal systems. Again, to support the bodily mass, vertebrates have immensely changed, reorienting limbs under the body to support weight, strengthening the vertebral column, and or expanding the rib cage to maintain an erect posture. And this also helps with lung expansion and their breathing mechanics. Okay, so the combined environmental and gravitational forces resulted in a dramatic reorganization in the skeletal structure of vertebrates. As you can see in my picture here, we have a skeletal structure of amphibians showing what adaptations were made. One of the major changes was moving the limbs from a lateral orientation, as in a fish, to the upright position underneath the body to support their weight and hold themselves upright. Dr. Vandenbrooks states, upright limbs that give support coming underneath the main skeleton operate in this new terrestrial realm, which additionally emphasizes how limb orientation was important to moving on land. In addition to moving limbs, other changes in the skeleton were also required to accommodate the demands of gravity and facilitate relatively efficient movement. Vertebrates initiated adjustments in their skeletal structure that simply reinforced the body enough to allow for repeated movements. The vertebral column underwent some of the most substantial changes, for example, separating the cervicals from the pelvic girdle and pectoral girdle, allowed for a neck that was flexible and could function independently. The neck development offered major advantages, especially in feeding, sensing the environment, and escaping predators. Changes in the ribs were also significant, as they contributed to posture in vertebrates on land, as well as reinforced the rib cage to facilitate lung-based respiration and coordinated skeletal structures with function. All of these changes show tightly coordinated. Sorry. It's late. I don't know what I was trying to say right there. Okay, so on this slide we have locomotor adaptations. This is showing the progression of early tetrapods and how they didn't completely abandon their ancestral characteristics. It says terrestrial locomotion became energetically costly. It says right here that tetrapods did not immediately abandon their ancestors' locomotor routes. They retained some characteristics of their aquatic locomotor styles, demonstrating a gradual transition from aquatic to terrestrial life. As Dr. Vandenbrooks states, these tetrapods retain an ancestral tetrapod gait, alternating their limbs back and forth as they undulate their body, suggesting early tetrapods still use some combination of limb movement and body undulation for mobility. This hybrid pattern of locomotion would allow some efficiency while still accommodating living with the constraints of gravity and the substrate on land. In addition to limb movements, modifications of the tail and axial skeleton were best supports for these early tetrapods for moving on land. They still had a tail, and it was quite elongated, as well as their bodies, but this contributed to their balance and stability and some propulsion for movement. As the result of lifestyle on land, the elongated tail provided a counterbalance to the head and forelimbs to some degree and helped stabilize the body when moving upright or walking across uneven terrain. Modifications at the axial skeleton, such as elongation of the vertebrae and reinforcement, also provided an increased flexibility and ability to force transmission, which would have supported the tetrapods' ability to coordinate limbs and body together when moving about on land. These supporting adaptations contribute to understanding early tetrapods' locomotion and the legacy of locomotion in this clade. Okay, let's see. This slide is covering respiratory adaptations. So we have a picture over here showing the carbon dioxide and oxygen exchange for a little frog. And it's showing the air breathing results in lungs supported by thoracic cavity expansion. It says respiratory adaptations were associated with shifts in skeletal and muscular structures, demonstrating the relationship of form and function in vertebrate evolution. After leaving the water, vertebrates could no longer take advantage of simple oxygen diffusion through gills, which are effective in an aquatic environment. They are inefficient in an atmospheric environment. Air breathing required the users of lungs and associated structures that could ventilate the lungs. For example, in amphibians, lungs evolved in a buccal pump, positive pressure system, which allowed this group to actively suck into their lungs by rhythmically depressing the floor of their mouth. Amphibians were also able to achieve this with modification to the thoracic cavity that allowed for expansion and increased muscular control, which allowed amphibians to efficiently ventilate the lungs while still allowing coordinated limb movement for terrestrial locomotion. In many amphibians, lung function is supported by cutaneous respiration. In some cases, more elongated amphibians have a higher degree of cutaneous respiration. Dr. Vandenbroek notes, the high degree of cutaneous respiration in amphibians requiring their skin to remain moist for gas exchange to take place. This dual style of respiratory strategy, lungs plus skin, aided amphibian efforts for oxygen demanded in a land environment while also minimizing evaporation in humid or moist habitats. Importantly, these respiration adaptations do not happen in isolation. Skeletal structures, i.e. the rib cage. So right here we have environmental pressures. Terrestrial habitats require posture, locomotion, respiration without water support. Animals navigate complex terrain, find prey, and avoid predators. So it's saying selective pressures results in skeletal and function adaptations. Environmental changes, particularly the shift from aquatic to a terrestrial environment, drove these adaptations. Animals needed to maintain posture, locomotion, and respiration without water support and be able to navigate more complex terrains, seek prey, and avoid predators on land. As Dr. Vandenbroek summarizes, locomotion became more costly. Prey are less dense, and more energy has to be utilized to actually get the resource that is required. Consequently, skeletal modifications, limb placement, and axial adaptations evolved to meet these selective pressures, enabling vertebrates to successfully exploit land habitats. In Module 3 and 4, Dr. Vandenbroek discusses various adaptations in amphibians and non-avian reptiles. For instance, in amphibians, he highlights the development of specialized skin structures that facilitate cutaneous respiration, allowing these organisms to thrive in both aquatic and land environments. Similarly, in non-avian reptiles, adaptations such as the evolution of four-chambered heart are emphasized. So right here, we have the world's smallest known vertebrate animal. It has made impressive adaptations to its environment. Its small body size allows it to live in leaf litter on the forest floor where it can be camouflaged and escape predation. This is likely an adaptation to the selective pressures in the predators of small size and a dense leaf-littered habitat. The central province of PNG, with its dense vegetation and humid conditions, is a favorable area for adaptation characters. It says the small body size may allow exploitation of microhabitats within the leaf litter, as there would be an abundance of resource with minimal competition. Here we have the Thermophis bailey, adapted to geothermic environments in high altitude habitats. It has several unique anatomical traits. The elongated and slender body structure allows for streamlined movement across rocky outcrops and promotes rapid swimming in thermal waters. The strong keeled dorsal scales improve grip on slick geothermal rocks and surfaces, while the smooth and wide ventral scales improve terrestrial movements and swimming. On this slide, we're going to discuss cardiovascular adaptations. This covers the three-chambered heart and how it allowed better separation of oxygenated and deoxygenated blood, and non-avian reptiles partial separation for more efficient oxygen delivery. So it talks about how the fish originated with a two-chamber heart and then adapted a three-chamber heart for better separation of oxygen and deoxygenated blood to improve delivery of oxygen to the tissues. The development of this system is an adaptation to living on land, where increased oxygen transport is a necessity due to higher metabolic demands than the aquatic organisms.